Hello my dear students, I warmly welcome you to CA Digital Classes. So now in this lecture, we are going to discussing another topic, that is similar matrices and problem based on the similar matrices. First of all, observe the statement, define similar matrices. Prove that similar matrices have the same characteristic polynomial. Okay, that is the second question. And the third question is, find the characteristic equation and eigenvalues of a 2 by 2 matrix, that is 2, 3, 3, minus 6. Here we have three problems. The first problem is we have to define the similar matrices. Okay. So after that, based on the similar matrices concept, we have to prove that similar matrices have the same characteristic polynomial. Here characteristic polynomial is nothing but a minus lambda I. A minus lambda I into x. A minus lambda I into x is called characteristic polynomial. Characteristic equation is nothing but whenever you apply det a minus lambda I into x equal to 0, that is called a characteristic equation. Characteristic equation. So the difference between characteristic equation and characteristic polynomial is, for polynomial we cannot make that value equal to 0. For characteristic equation we can make the determinant value equal to 0. A minus lambda I equal to 0. Now we are starting the definition of this problem. Similar matrices definition: if A and B are n by n matrices, A and B are square matrices, then those two square matrices are said to be similar matrices, or capital A is said to be similar to capital B if there exists an inversible matrix capital P such that the relation between them is P inverse A into P is equal to capital B, or A is equal to P into B into P inverse, then A and B are called as similar matrices. Here similar matrices means, first of all you have to take one square matrix capital A n by n, and at the same time capital B also one square matrix n by n, same order matrices, where n is equal to greater than or is equal to 2, where n is always greater than or is equal to 2. Now this A and B two matrices are said to be similar matrices. What is the condition? Condition is, if there exists an inversible matrix, that is capital P, for this capital P inverse is also existed such that, so this capital P is also one square matrix, this capital B has some inverse, then the condition is capital B we can write it as P inverse capital A into P, or else we can write capital A as product of P into B P inverse. Whenever you can write capital A and capital B in this format, so then we can say that A and B are the similar matrices, or A is similar to capital B or B is similar to capital A. So the main concept is there exists one inverse matrix, there exists one inversible matrix capital P. So that is the definition of the similar matrices. Next point is, capital B is similar to capital A, then Q inverse B into Q is equal to capital A for any inversible matrix capital Q. Okay, so here capital A is similar to capital B ante manam em cheppam, oka P anedi oka inversible matrix ani cheppam. Similarly, to say that capital B is similar to capital A, okay, capital B is similar to capital A, what is that condition? There exists one inversible matrix Q, Q inverse B Q equal to capital A. This is the condition. Okay, so whatever the matrix you can take capital P or capital Q. Okay, so the next point is, changing matrix from capital A into P inverse AP is called a similarity transformation. Okay, the total phenomena or the total process is called similarity transformation. And while solving problems based on the similar matrices, to find the similar matrix of capital A, okay, so we need to prove this property P inverse A into P. That means from capital A to P inverse AP, that process is called similarity transformation. Likewise linear transformation. So that is called similarity transformation. Why? Because the main concept is similar matrices. That's why we are calling it as a similarity transformation. So that is the definition regarding that. Next question is, so we can also mention the examples also. Okay, so therefore similar matrices have same characteristic polynomial. Okay, similar matrices have same characteristic polynomial is the other question. Let capital A and B be two similar matrices and P of T be the kth degree polynomial. P of T be the kth degree polynomial. Since A and B are similar matrices such that P inverse A into P is equal to capital B. A and B are similar matrices, or we can say that A is similar to B, then we can apply this formula P inverse A into P equal to capital B. A is similar to capital B అంటే ఆ A అనేది మనకి ఏమొస్తుంది, మిడిల్ లో వస్తుంది. B is similar to capital A అంటే ఆ B అనేది మనకి ఏమొస్తుంది అంటే మిడిల్ లో వస్తుంది. ఏదైతే సిమిలర్ అని చెప్తున్నామో క్యాపిటల్ మ్యాట్రిక్స్, ఆ మ్యాట్రిక్స్ అనేది మనకు ఈక్వల్ టు ఆర్హెచ్ఎస్ లో రాసుకుంటాం అనమాట. సో దేర్ ఫోర్ దెన్ లెట్ P be the n by n inversible matrix. Here P of T is the polynomial amma. Order of polynomial is kth degree. Okay, and P is the one n by n inversible matrix. So అది మీరు కొంచెం గుర్తుపెట్టుకోండి. కన్సిడర్ determinant of capital B is equal to determinant of P inverse AP. Okay, so why? Because capital P is a inversible matrix. Then to say that A and B have the same characteristic polynomial. Okay, same characteristic polynomial. Why? Because A and B are the similar matrices. Direct we are taking that condition B is equal to P inverse AP. Okay, for this condition only on both sides we are applying that the determinant. Apply the determinant. So determinant of B is equal to determinant of P inverse AP. So since by equation number 1. So determinant of B is equal to, apply the determinant value individually. From the properties of determinants we can also apply this property, determinant of P inverse, determinant of A, determinant of P. Okay, so here from these two conditions determinants property also satisfies the commutative property. So therefore determinant of A into determinant of P inverse into determinant of P. Next, determinant of A will be as it is. For these two values we can write determinant common P inverse into P. You know very well where P is a inversible matrix. So therefore P into P inverse is equal to capital I. Determinant of identity matrix is equal to 1. So therefore 1 into determinant of A is equal to det A. Det to B is equal to det to A. ఈ కండిషన్ గుర్తుపెట్టుకోండి. And the characteristic polynomial for matrix B is given by, the characteristic polynomial for matrix B is given by P of B. P of B is equal to, equation for the characteristic polynomial is mod B minus lambda I. So therefore consider mod B minus lambda I is equal to, substitute that capital B value from equation number 1 and lambda I value will be as it is. So in place of capital I, from this condition, since we have P inverse into P equal to I na, so I am substituting that value again. So for that, after applying that capital I is equal to P inverse into P, so now I am taking P inverse into P common. Okay, so P inverse common, then you will get A into P into lambda P. Take P also common, then you will get P inverse into A minus lambda into I. A minus, here only lambda will remain, but lambda is a parameter or constant. But we have to apply that identity matrix for that. Why? Because here capital A is the matrix. To apply the subtraction, so for that lambda we have to multiply with the identity matrix. So therefore A minus lambda into P. So therefore again if you multiply with P inverse and P, you will get this value only. Okay, so therefore from this condition we can observe that. So now separate the determinant value. You can get that det to P inverse into det of A minus lambda I into det to P. So this value will get cancelled almost. So then you will get determinant of B minus lambda I is equal to determinant of A minus lambda I. Since already we have det to B is equal to det to A. Okay, so here determinant of B minus lambda I is equal to characteristic polynomial of capital B, and determinant of A minus lambda is equal to characteristic polynomial of A. So therefore both are equal. So therefore P of A and P of B are similar. Okay, so therefore have the same characteristic polynomial. So then we can say that P of A and P of B are similar. Hence, the similar matrices have the same characteristic polynomial and A and B have the same eigenvalues with the same multiplicities. Okay. So whenever characteristic polynomials are equal, then same eigenvalues will exist with the same multiplicities. Multiplicities అంటే ఒక eigenvalue అనేది మనకు రిపీట్ అవ్వచ్చు. In the previous lecture we got lambda is equal to 2, 2 and 9. ఇక్కడ 2 అనేది ఏంటంటే 2 times రిపీట్ అయింది. సో therefore ఇప్పుడు lambda equal to 2 కి మల్టిప్లిసిటీ ఎంత అంటే 2 అని చెప్తాం. lambda equal to 2 కి మల్టిప్లిసిటీ 2 అని చెప్తాం. అదే lambda is equal to 9 కి మల్టిప్లిసిటీ ఎంత అంటే 1 అని చెప్తాం, ఎందుకంటే అది ఓన్లీ 1 టైం మాత్రమే రిపీట్ అయింది కాబట్టి. So in that format, similar matrices have the same characteristic polynomial. So therefore, next you can observe the note point. The matrices capital A and B have the same eigenvalues. And మీకు ఒక డౌట్ రావచ్చు from the last point. Similar matrices have the same eigenvalues with same multiplicity అన్నాం. ఇక్కడ చూడండి, ఇక్కడ A and B అనే 2 matrices ఉన్నాయి. ఆ 2 matrices కి సేమ్ eigenvalues ఉన్నాయి. బట్ ఏ అండ్ బి ఆర్ నాట్ సిమిలర్ మ్యాట్రిసెస్. ఇది కూడా ఒక నోట్ పాయింట్. అంటే సిమిలర్ మ్యాట్రిసెస్ అయితే సేమ్ ఎయిగన్ వాల్యూస్ సేమ్ మల్టిప్లిసిటీస్ ఉంటాయి, బట్ సేమ్ ఎయిగన్ వాల్యూస్ ఉన్నంత మాత్రాన ఆ రెండు మ్యాట్రిసెస్ సిమిలర్ మ్యాట్రిసెస్ అవ్వాలని మాత్రం రూల్ లేదు. సో దట్ ఈస్ ద నోట్ పాయింట్. నెక్స్ట్ సెకండ్ నోట్ పాయింట్, ఇఫ్ క్యాపిటల్ ఏ ఈజ్ ఎ రో ఈక్వివాలెంట్ టు క్యాపిటల్ బి. ఓకే, సో వీ కెన్ సే దట్ క్యాపిటల్ ఏ ఈజ్ రో ఈక్వివాలెంట్ టు దట్ క్యాపిటల్ బి whenever b is equal to capital E into A, whenever b is equal to capital E into A for some inversible matrix capital E. Okay, so therefore similarity is not the same as row equivalence. Why? Because the row operations on a matrix usually change its eigenvalues. For example, if you get a matrix capital A, to get the echelon form we can gradually apply the row operations. After applying that, you will get that the one echelon form of that matrix. For that echelon form matrix, you will get the different eigenvalues. That is only the row operations on a matrix usually change its eigenvalues only. That is the similarity is not same as the row equivalence. So next given problem, the third problem is, given matrix is we have capital A is equal to 2, 3, 3 minus 6. The characteristic equation is given by det of a minus lambda I equal to 0. So substitute the corresponding values. Okay, so simplify them. You will get one quadratic equation in terms of lambdas. Lambda square plus 4 lambda minus 21 is equal to 0. For that lambda, if you simplify, then you will get lambda is equal to 3 and minus 7 are the eigenvalues. Okay, therefore eigenvalues are 3 and minus 7. Those are the eigenvalues. So for this eigenvalues, we can also find the corresponding eigenvectors. Okay, for example, if you take lambda is equal to 3, then a minus 3i is the a minus 3i gives the one eigenvector. If you take lambda is equal to minus 7, then a plus 7i gives the second eigenvector. In this format, we can proceed. So okay, so therefore this is the total explanation of this lecture. So similar matrices have the same characteristic polynomial and problem based on the eigenvalues. So therefore I hope you understood this lecture very well. So with this lecture, this unit videos are completed. So in the next lecture we are coming with another unit videos. So make a perfect practice, prepare well. Until bye. Thank you.